Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is CSA S16 2019 Steel Design in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Cho will be your moderators, answering any questions you may have. They are both technical support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So regarding the content over the next hour today, I do want to begin in our main FEA program, RFEM 6. So here we'll review our structure as well as the loads that have already been applied. I then want to take advantage of our first add-on, which is called Stability Design, to troubleshoot instabilities within the program. We'll then move on to the CSA S16, and specific to the 2019, we have the new Annex O.2 stability requirements and how we can apply those in our example model today. We'll then utilize within RFEM the steel design add-on. So this will be specific to the actual design portion of our members, specific to the CSA standard as well. We'll see how we can input our data. And finally, we'll run a full analysis and design. We'll take a look at the results. So we'll switch over here to RFEM 6, and as mentioned, we've already modeled the structure here just for the sake of time. So before we get into reviewing this structure, I want to right-click here on the model name within my navigator to access the base data. So this base data will be what first pops up when you create a new model. And under this second tab, these are all of our optional add-ons. So notice that none of them are turned on right now. So everything that you'll see in this first portion of this webinar is involved within RFEM alone without turning on any of these add-ons. Under the third tab, standards, we are going to generate our load combinations automatically according to the NBC 2015 standard. We are working in development on the 2020 standard, so that should be released fairly soon. But we also have access to all of our other international standards like the ASCE 7, the Eurocode, and many more. So once this base data has been defined, we'll review the cross sections within the model. So over on the left, we can see all of the available cross sections here, including our moment frames, which are going to utilize W250 by 80 sections. We have some tube sections, HSS 127 by 127 spanning between these moment frames. We have our lateral bracing here, which is going to be single angles. And then we have some pretty slender HSS columns at the front and the rear of the structure. Now notice that for these main moment frames here, these particular beams, we do have these set to a taper. So if we double click on these under the second tab, we can define a taper for any of the members, either at the start of the member or end of the member, and some additional options here. We even can set the alignment here to the top of member. So notice that the members start. I've converted this W250 by 80 to a parametric section and increased the depth to 500 millimeters, and then we transition back to the W250 by 80. We also have our materials listed here. So most of the HSS sections will utilize the A1085. Our single angles will be 350W, and our W sections will be A992. What else is unique about this structure are the various member types. So if we visit our navigator and the second tab in particular under display, this is going to control everything that we're viewing here in the graphical display. And if we scroll all the way to the bottom, we can actually render the colors of the model according to the member type. So notice these various member types are now color coded here. So we have our general beam elements, which is nothing more than just a standard beam or column. If we double click on one of these, the member type is set here under this first drop down. We could activate hinges to release moment. If we leave this unchecked, everything is considered fully fixed. But we also have what we call truss elements. So the member type is set to truss. Notice that this hinges is now grayed out. So internally, we're going to apply that moment release for truss elements. And finally, we have our lateral bracing here, which are tension only. So exactly as it sounds, these members can only take tension forces. If they have any compression, they'll be deactivated within the analysis. RFEM is that nonlinear analysis program, so if tension forces are reintroduced in a subsequent iteration, we can reactivate those members. So now that we've gone over a little bit about the structure, including the sections and materials, let us take a look now at our loads and load cases. So I will activate here my load cases and combinations dialog box. Under the base tab here, this is just reiterating that we are going to generate our load combinations automatically according to the NBC standard. When this option is turned on here, the program will automatically generate all of our load combinations according to this standard. Now, alternatively, we can turn this off if we would prefer to manually create the load combinations. The load cases are listed here. So for example, 4 simple load cases for today, we have dead load with self-weight automatically turned on here. The action category is set to dead load. This is specific to the NBC. We also have snow load, wind in the X, and wind in the Y. So the program will automatically generate for us what we call design situations. These design situations are needed a little bit later on when we do activate that steel design add-on, but it also was going to group together all of our load combinations. So notice that we have an ultimate limit state design situation. This is going to be all of our factored load combinations. And if we'd like to see what this means or what it's referencing, we can click on this little info button here to see directly from the NBC standard those factored load combinations here. Now we have 3 serviceability design situations as well. Again, we can click on this little info button. These are going to be our unfactored load combinations. If we don't want to use all 3 serviceability design situations, we can always uncheck the active in the upper right hand corner, or we could delete it altogether with this button down here at the bottom. But notice for these design situations, we have the option definition set down here, and we'll actually be in this dialog box quite a bit today. I just want to point out that initially our static analysis settings are set to second order by default. If we use this drop down, you can see we can modify this to a linear first order, or if we have cable elements or fabric membranes, for example, then we would be running a large deformation analysis, but the default is second order to account for those P delta effects, so something to keep in mind there. If we jump to the load combinations tab, we can actually see the individual load combinations listed out, again, each belonging to that specific design situation. So here in red, we have our factored load combinations belonging to our first design situation, and then all of our unfactored load combinations belonging to those 3 serviceability design situations. Each one is showing here that it's going to be run according to a second order analysis because we've already defined that under the design situation. But by all means, you can come in here and make individual settings for each load combination if you prefer. Okay, so now that we have our load cases and combinations set up, let's review the loads that are actually applied to this structure. So we can use our drop down to take a look at the dead load and to see the dead load actually applied here to our steel frames. Now, I took advantage of what we call our load wizards. Over here on the left-hand side on our navigator, we can access the load wizards, and we see here member loads from area load. So that's what we're displaying at the top of our structure. If I double click on this, what we can do here is to specify the load direction, and we can see here it's in the vertical Z based on the global axes shown here back in the model. And I've defined the load magnitude at -1 kilonewtons per meter squared. Under the geometry, these are the 4 corner points that are going to define the left plane and the right plane. And then I took this a step further where we can actually exclude members from this generated area load. And I graphically selected these 3 members here, which we can somewhat see over on the left-hand side. And not only will the program exclude these 3 members, but it will also exclude all members parallel to it. So this is just a bit of a time saver so we don't have to individually select each member. So once this is complete, what we see here is this generated area load where we can right click to display separately, and notice that my load is now being distributed only to those main moment frames here. The tributary area is automatically accounted for, so nothing to do further here for dead load. We can right click and turn off the display separately to go back to that previous view. As far as snow load, exact same concept here. The only difference is that I modified the load direction in the projected Z direction, so we can actually account for the angle here of our roof and modify the loading according to that angle. The load magnitude was also adjusted to negative 1.5 kilonewtons per meter, same geometry here. So when I take a look at this in the model and I display separately, should look fairly similar to our dead load, but just with adjusted load magnitude. Now, finally, we have our wind load. So we are working in development to generate the wind loads automatically, as well as snow loads according to the NBC standard. They will be available under the load wizard. We hope to release that fairly soon, but for now, we will need to manually apply these loads to the structure. And I've done so with those same member loads to area load generator. You can see here I just modified where my planes are located, as well as the magnitude. We can right click here to display separately. We're assuming our wind load is flowing here from left to right based on the global x-axis, and we can see all of those member loads assigned here. We can also take a look at wind in the Y direction. So we're assuming wind flow here from right to left based on the global Y axis. And again, right click to display separately, and we can see those member loads attributed to each of those vertical members as well as horizontal members for this particular plane. So now that we have applied all of the various loads under the specific load cases, we can view here our load combinations, and we have the ability to display all of these loads on the structure at once, including the applicable load factors from the NBC. So what I would suggest doing early on in the model is to complete most of the modeling, the loading, and it's always a good idea to run a quick calculation before we get too far into it to ensure that we don't have any modeling errors. So what we can do is to jump to load combination number 2 here, 1.25 dead plus 1.5 snow. And I'm just going to run this single load combination. So when I run the calculation up here in my toolbar, what we'll immediately notice is that the program actually doesn't solve. We get an error message and it says we have some errors and warnings, please check the table. When we look at the table and we click down here in the cell, we see that the program's telling us that the stiffness matrix is singular. The structure is unstable about FE mesh node number 59, about the global x-axis, and we can see where that red arrow is pointing. So that red arrow can actually help us troubleshoot instabilities a lot of the time, but that's not always the case. If we have more of a global issue, this red arrow may not be so helpful. But in this particular case, if we zoom in, we see, okay, everything appears to be connected properly. We just have this pretty slender column framing up into the beam with our HSS tube in between frames. So I really don't know how to troubleshoot any further just by simply viewing the model. So this is where we want to take advantage of our first add-on. So I right click under my base data to go back to this dialog box that we previously saw. And under the add-ons, we'll make the clear distinction here that we now want to activate the structure stability add-on. When I click OK, everything seems like nothing is much really changed within the model, but what we can do now is to go back to load cases and combinations dialog box here. And under load combination number 2, we now have the ability to calculate the critical load utilizing that structure stability add-on. So when I turn this on, we have some additional settings here in this dialog box that pops up. So the stability analysis add-on will actually run an eigenvalue analysis, and we can view all the different eigenvalues set here. The problem is if I try and run this calculation, I'll get another error, just simply because load combination 2 doesn't solve either. So we have this feature over on the right-hand side where we can actually calculate without the applied loading to check for instabilities by the mode shape. So notice the number of eigenvalues is now grayed out. We leave this option active. I click OK. I can click calculate while I'm here within this dialog box. And once again, we solve for load combination number 2. We still get an error, but now we do have some results for that stability analysis add-on. And we immediately see where the problem lies. So it almost appears as though this column is not connected to the member. Well, perhaps I turn off my results here and I go into a wireframe view and I zoom in much closer than what I was previously, and I actually see that these two nodes are not connected. So this is a simple fix where we can just simply drag and drop that node to connect to that particular beam, and that should address the issue. So we can see how that stability analysis add-on can be used here to kind of troubleshoot unconnected nodes, for example. So now that we've corrected that modeling error, let us go back to load combination number 2 here, and we'll turn off the structure stability add-on. We'll try and calculate once more. So we've addressed that modeling error, we run the calculation, and unfortunately what we see is still another instability. So I click OK and I click down here in my error message, but notice that my red arrow has now moved. I have an instability about FE mesh node 128 about the global axis X. Well, at this point, I've already ruled out any modeling errors. All the nodes are connected, so all the supports are connected. So what can we do here? Well, the first suggestion is remember that we're running load combination number 2 here according to a second order analysis. The best approach, if we've ruled out modeling errors, is to change this single load combination to a first order analysis. And let's see if the model solves by changing this analysis type. So we click calculate, and what we see here is actually that the model solves just fine under first order. So now we need to move on to troubleshooting for this second order analysis instead. Well, once again, we can take advantage of the structure stability add-on. So we reactivate this for load combination number 2. Let's go into the detail settings here. Now I'm going to turn off this option over on the right-hand side now. The reason why is because we can run an eigenvalue analysis because load combination number 2 solves just fine under first order. Perhaps we increase this to show the number of lowest eigenvalues as 10. We click OK and we click calculate. So the program will run through that first order analysis, but now it's going to run an additional eigenvalue analysis to show us the first 10 failure modes of our structure. So we use our drop down on the left to not look at the static analysis, but let's take a look at the stability analysis. And sure enough, here are our 10 different eigenvalues shown here in the drop down. We also see it down here in our table under stability analysis. And the first failure mode shape looks to be this very slender column buckling in plane. If we look at the second mode shape, same column buckling out of plane. We take a look at the third mode shape. It seems to be the same column just on the other side. And if we look at the critical load factor, we immediately see what the problem is. It is 0.67. This means that the structure can only take 67% of the loads from load combination number 2 before we're going to see this flexural buckling failure of these slender columns. So anything under 1.0 is always a problem. So how do we address this? Well, probably the easiest fix is to increase these cross-section sizes. I think we can all agree just by looking at it, they're much too slender. So let us highlight all of these members. We can double click here, and under the section, we can use our drop down to change these to an already defined cross section in my model, a W130 by 24. So let's completely change this to an I-beam here. I click OK. It's asking me to clear my results. That's fine. And now we can see the structure looks quite a bit better without those very slender members. So we go back to load combination number 2. We change this back to second order, and we can go ahead and run the structure stability add-on just to see how our results vary. When we modify this, what we see here is that second order should solve just fine. We also see here the stability analysis. So we're taking a look at the static analysis. If we jump down to the stability analysis once again, and we take a look at our first failure mode, it once again is this column, But notice that my critical load factor is now 9.92. So what this means is that the structure can handle over 900% of the loads from load combination number 2 before we see some stability failure mode as we see here. So again, that structure stability add-on can be incredibly helpful, not only for simple modeling errors of unconnected nodes, but when we're trying to troubleshoot something that we really can't determine just by looking at the model itself, such as failure modes under stability, we could certainly utilize that add-on. All right, so now that essentially our modeling, our loading is complete, let us jump back to the PowerPoint here, and we'll discuss specific to the 2019 standard stability considerations. And we know in clause 8.4, the code tells us that the structure absolutely has to be defined or designed for stability. Looking at 8.4.1, the code tells us that stability shall be provided for the structure and all elements of the structure, considering topics such as deformation, second order effects such as big P delta, little P delta. We have geometric imperfections, stiffness reductions, and uncertainty in strength and stiffness. Well, within the code, in particular clause 8.4.2, we are given two methods for the analysis and design for stability. The first is this simplified stability analysis method in 8.4.3. So for those of us that have been doing steel design for quite some time according to the CSA standard, this is probably nothing new. But within the 2019 standard, we know that there has been an alternative method added, which is stability effects and elastic analysis in Annex O, which is laid out in clause 0.2. And this is what we're going to be focusing on today and how we can apply that directly to our structure. But before we do, let's discuss the simplified stability requirements. And this method, again, is given in 8.4.3. The first requirement is P delta effects. This is explained further in 8.4.3.2, and we have two options to consider these second order effects. The first is simply a second order analysis, and we saw back in RFEM for our load combinations as well as what we set under the design situation that all of those load combinations will automatically be solved for according to second order. So this is certainly our approach here. The alternative method is to apply what we call the U2 amplification factor, and this is given in 8.4.3.2b. So we take this amplification factor and we apply it to the member's axial loads and bending moments from the first order analysis. So perhaps your software only has the capabilities for a first order analysis, or you're doing hand calculations, then you would probably be utilizing this U2 amplification factor. Now, the second requirement under the simplified method is the notional lateral loads in 8.4.3.3. Actually, let me back up one second. I did want to discuss here P delta effects in this diagram over here on the right-hand side. So we all should be familiar with P delta effects. And again, within RFEM's approach, all of this is kind of done under the hood here to account for this. But we have this vertical member here with the applied gravity load P. And with this applied gravity load, we may have additional lateral loads V. Well, inevitably, this member is going to deflect here a distance of delta. And when the member deflects, that gravity load P will also deflect. So we're inevitably going to get this induced moment on the member P times delta. If we take this explanation a little bit further, we also have P little delta. This just means that the member is going to have some distortions and curvature along the member length, and it will deflect a certain distance here of little delta. So P little delta effects might be something also to consider. Now, again, the simplified analysis method only addresses, as we've already discussed, big P delta effects. But again, you would either want to account for that directly within the analysis or with that amplification factor. Now, with these notional lateral loads, the second requirement, we have here the notional lateral load applied in the same manner that we would see, such as V shown over here on the right-hand side. We take that factored gravity load, so let's say that's P, we multiply by 0.005, and we apply it to the top of the member laterally. Now, these notional loads should be applied in the same direction at all levels. They also should be applied independently in the 3D structure's orthogonal direction. So when we're referring back to RFEM, we're talking about the global X and the global Y directions. And it really needs to be applied to create the greatest destabilizing effect. And you'll hear me say this several times today. This just simply means if we have wind in the X direction, we also apply our notional loads in the X direction. If we have wind in the Y, our notional loads should be in the Y direction. And one last thing to keep in mind is that if we are applying notional loads to the top of the member, we do want to apply an equal and opposite load to the bottom of the member to correct that fictitious horizontal reaction at the base of the member. We don't want to over design our foundation here. This is really for the member design. Okay, so now that we have taken into consideration the simplified stability analysis, we have this alternative now in Annex O laid out in clause 0.2 for stability effects in the elastic analysis. And there's several requirements, some similarities, some differences here from this simplified method. The first is geometric nonlinearities for second order effects according to 0.2.2. So we do want to account for big P delta here, and we saw this on the previous slide. The program will automatically account for that, no problem. But it does also mention P little delta effects that the simplified method did not. So there are conditions to neglect P little delta effects, and these are laid out in 0.2.2 A through D. So if you do meet those requirements and you are designing according to Annex O, perhaps you don't necessarily need to consider P little delta. If you do include P little delta, the advantage here is that this factor given to us in chapter 13, which is under member axial compression and bending design, U sub 1, we can set this equal to 1.0. Well, this factor is used to account for second order effects due to deformation between the member ends. So again, the advantage of including P little delta in the analysis is that we can automatically set this factor to 1.0. So we might be wondering, well, we know probably RFEM includes big P delta, but does it include little P delta as well? Well, we actually have a knowledge base article number 1759 directly on our website, and I have set the hyperlink here. So if we access this knowledge base article, we can see that the title is consideration of P little delta second order effects in RFEM 6. So we've taken an RFEM model and we've actually compared it to the benchmark problem set forth within the AISC 360. And what we found out is that P delta is automatically included, both big P delta and little P delta. And the advantage of RFEM is that you don't need to subdivide the member into multiple segments. You don't need to add additional nodes along the member length. You can keep this member as one continuous segment, and that P little delta will be accounted for. And if you're interested to take a look at this article, you can zoom in here and we can actually see the ratios comparing the AISC to RFEM, and we see those ratios are very, very close to 1.0. This PowerPoint will be available to you on our website after the presentation, again, with the hyperlink to this knowledge base article if you'd like to check that out further. All right, let us move on to imperfection requirements. So geometric imperfections is addressed in clause 0.2.3, and the code tells us that member and local geometric imperfections can be neglected for the elastic analysis. When we're talking about member and local geometric imperfections, I put a little picture over here on the right-hand side. This is really looking at the individual member itself. So perhaps we convert the 1D member into 2D surfaces for an FEA analysis, and we directly modify the FE mesh to consider topics like manufacturing defects. Well, when we're designing according to Annex O, we can actually neglect these. Rather, we're concerned with global geometric imperfections, and there's a couple listed methods for these. Now, before we look at these methods, there are a couple criteria where we can completely neglect global imperfections for lateral load combinations only, and these are listed in 0.2.3.1. The first is if gravity loads are primarily supported by vertical elements. The second is if the first to second order story drift ratio with reduced member stiffnesses is less than 1.0. 0.7. So we'd want to reduce our member stiffnesses. We'll get into this in just a few minutes. We run the first order analysis, and then we change that analysis type to second order. We take a look at the story drift. If we meet these ratio requirements, then we can also neglect those global imperfections. Now, if we do need to consider the global imperfections, again, there's two methods for this. The first is direct modeling in O232. This is where we would physically displace the member intersection points. And for this, we'd probably refer to the permissible erection tolerance values set forth in clause 29.3. And we're mainly concerned here with column out of plumbness tolerances. And that limit is set at 1/500. So what we would physically do is go into our RFEM model and to create that column out of plumbness by modifying the intersection points. Now, you can imagine this is difficult and it's going to require multiple different models. Again, if we're trying to create that greatest destabilizing effect, we should have column out of plumbness in the X direction for winds in the X, column out of plumbness in the Y for winds in the Y. If you have seismic loads, it could go on and on. So rather, the alternative method number 2 with notional lateral loads is probably the easier approach laid out in O233. Now, we've already discussed notional lateral loads under the simplified stability method. A lot of similarities here. But notice one big difference is that we're actually going to take our factored gravity load and multiply it by 0.002. So we might be wondering, well, why does the simplified method have that factor set at 0.005 versus the 0.002 factor in Annex O? Well, the 0.002 factor only accounts for the effects of global geometric imperfections, whereas the simplified method with 0.005 accounts for the global geometric imperfections, but also accounts for other effects such as inelasticity. So that's why we're seeing that difference here with that modification factor. Now, once again, we want to apply in the direction with the greatest destabilizing effect, as we already discussed. So we'll see in just a minute in RFEM, we can automatically apply these notional loads with what we call imperfections. And we have two imperfection types. The first is what we call initial sway imperfections, or we could think of this as column out of plumbness, where we can kind of modify those vertical members here with the notional loads. But alternatively, or in addition to, we also have initial bow imperfections. So if we wanted to consider the member out of straightness, we also have the imperfection capabilities in RFEM for this as well. Now, we're not going to be addressing the bow imperfections on the right-hand side here. We're really only concerned with today this initial sway or column out of plumbness. So we will go back here to the RFEM model to see how we can apply those notional loads to our vertical members here. Well, I'll begin by selecting all of my vertical elements by holding down my shift key, and I'll create a user-defined visibility here for only my columns. And I'm going to right click, and under the right click options here, we can turn on our local axis system of each member. Now, to apply the notional loads, we go back to our navigator, and what we should see over on the left is a folder called Imperfections. And the first option under this folder is Imperfection Cases, where we can right-click to create our new imperfection case. And the first case is going to be imperfections in the positive X direction. Our second imperfection case is going to be imperfections in the Y. So with these imperfection cases, we have many different types available, but we're focusing here on local imperfections to be applied directly to the members. Now, under the assignment tab, remember we're creating the greatest destabilizing effect. So my imperfections or my notional loads in the X direction should be assigned to my wind in the X direction. And my imperfections in the Y should be applied to my wind in the Y. So notice all of our generated load combinations are already listed here kind of in the background. And the program's intelligent enough to apply these imperfections to our gravity load combinations, but my imperfection in the Y will only be applied with my wind in the Y. We'll never see imperfections in the Y applied with wind in the X. This is just creating more load combinations that aren't going to be controlling, so it's really not something that we need to include. So once we have created the imperfection cases, we click OK, and it's asking me to clear my results. We should now see those available under the local imperfection tree option over on the left. We actually need to now apply those notional loads to each of these vertical members. So under my first imperfection case in the X, I can double click on member imperfections to open up this dialog box. The imperfection type is initial sway. Remember, we talked about initial bow, but we're going to focus here on the initial sway. The definition type can be set to the CSA S16. Now there's two options here, current or gravity load. When we select current, the program is simply going to take the applied gravity loads in the current load combination to apply the notional lateral load. Alternatively, if we chose gravity load, we could import in the axial forces from some other load case or combination here. Perhaps we want to take a little bit more conservative approach and apply the notional loads for the worst case consideration. We'll be utilizing the current option here. Now we need to apply these notional loads based on the member's local axes, which we've turned on here in the background. So the imperfection direction in the global X direction will actually be the member's negative Z axes, which we can select here within this dropdown. Now the notional load coefficient, 0.005 is the default from the simplified method. Let us modify this to 0.002 from Annex O. And then we can graphically select all of our vertical members shown here. You can see they're now listed. I click OK. I click OK. I can cancel out of this visibility mode and turn on the display of my imperfections to now see this column out of plumbness in the global X direction. We do the exact same thing for our imperfection in the Y. It's going to be the initial sway with the definition type of the CSA S16. The difference here, though, is that we now want to apply this in the member's positive local Y direction from our dropdown. We are going to modify the load coefficient to 0.002, and then we are going to apply this to only our vertical members here. So notice I'm not applying to any of the additional members, but only those vertical columns. I click OK through these dialog boxes, and now we see the out of plumbness in the global Y direction. So I can right click here to turn off the local axis system. We've now applied those notional loads to the member. There's one more quick step that we want to look at here. If we drop down to one of our load cases or combinations, we can choose the button here to edit the active load case to bring us back into our load cases and combinations. Under the design situations, remember I said we would be in these options quite a bit today. Let us take a look at the definition type here for a combination wizard. Remember that we have set this to second order analysis, already meeting those requirements from the CSA standard, but we also have the option turned on automatically to consider the imperfection cases. So those imperfections will automatically be considered for all of my factored load combinations. But here's the problem, that all of my serviceability design situations and load combinations also utilize the same definition number 1 here. I do not want to apply those imperfections to my serviceability load combination. So how can I modify that? It's quite simple. We can just simply make a copy of this existing definition number 1. So now we have our new definition number 3. We're still running according to second order analysis, but I'm going to turn off my imperfection cases. I click OK, and now from my serviceability design situations, I hold down my Shift key, and I can use this drop down to assign them to definition number 3 here that does not include imperfections. But if I go back up to my ultimate limit state, it's utilizing this first definition type that will include the imperfections. Well, now if we look at our load combinations, we see quite a few more load combinations for our factored situation here. For example, if we look at the first 3 load combinations, they look identical with 1.4 dead. But notice the first is 1.4 dead without any imperfection. The second is 1.4 dead plus imperfection in the X. And then my third is 1.4 times plus imperfection in the Y. So when looking at some of these additional lateral load combinations, we should see one without the imperfection, but the first, wind in the X, will only include imperfections in the X, and wind in the Y will only include imperfections with the Y. So again, the program has that intelligence to correctly apply those imperfections to the correct load combinations. If we jump down to our serviceability, notice imperfections is turned off for all of them, and that's exactly what we wanted. Okay, so now that we have applied the notional lateral loads to the structure, let us go back to the PowerPoint here to discuss the final requirement of reduced stiffnesses. So reduced member stiffnesses are addressed in clause 0.2.4. And these are to account for initial geometric imperfections. If you remember, we neglected those with the global geometric imperfections on the previous slide. We also want to account for inelasticity and uncertainty in strength and stiffness. So how we do this is we apply a couple factors to the member's axial stiffness, EA, as well as the member's flexural stiffness, EI. The first reduction factor is 0.8, so that's fairly straightforward. The second reduction factor is tau sub b, and tau sub b is dependent on the factored axial force, so what's the axial force on the member from the applied loads, as well as the axial strength of the member itself. And we can see over here on the right-hand side directly from the standard that depending on what this ratio is, this is going to affect our tau sub b. So any factor or any ratio less than 0.5 tau sub b will be equal to 1.0. When this ratio is greater than 0.5, then we need to use this iterative calculation here to determine what that reduction factor should be for tau sub b. We will find here a lot of similarities to the AISC, Chapter C, the direct analysis method. One big difference, though, that you'll notice is that in the AISC, tau sub b is only applied to the flexural stiffness. The CSA, on the other hand, applies tau sub b to both the axial stiffness and the flexural stiffness. So that's one difference we'll find between those two standards. Now, we should apply the stiffness reductions to all members that contribute to the lateral stability of the structure. But if we're picking and choosing which members to apply the stiffness reduction to, this could lead to localized distortion. So the code goes on to tell us it's really recommended just to simply apply these reduction factors to all members within the model. Additionally, if the member's shear stiffness, GA, and the member's torsional stiffness, GJ, contribute significantly to the lateral stability, then these stiffness reductions should also be applied to these stiffnesses. So it would be up to the engineer to determine, should we also reduce the shear and torsional stiffnesses as well. Now, these reduced member stiffnesses are not applicable for serviceability, so we're talking about drifts, deflections, vibrations, natural periods. We want to keep the full stiffness for these serviceability checks. So once again, we'll go back to RFEM to see how we can apply these reduced stiffnesses to our structure today. We go back to our load cases and combinations, and once again, under the design situations, we will revisit the combination wizard options here. So it's kind of nice that all of these stability requirements are all really maintained here in this single dialog box. And to consider the stiffness reduction, we have here what's called a structure modification. We're going to turn this on for this first definition type here, and we create a new setting that's going to be applied specifically to our members. We get a new tab here for members, and we use our drop-down box to create a new member stiffness modification. And now we have this additional drop-down here where we can directly select the CSA S16 standard. We give reference directly to clause 0.2.4. And here is where the program can actually apply and determine this tau sub b based on these iterative equations set forth in Annex O to each individual member. Now, alternatively, if we want to just use 1.0, we can set that to 1.0 for tau sub b for all members or whichever members we select. But for now, we'll leave this as the iterative option here to refer to the standard equations. We also see that 0.8 factor. So both 0.8 and tau sub b will be applied to the axial and bending stiffness. If we've decided too that the shear and torsional stiffness contribute to the structure's lateral stability, then we'd want to go ahead and turn those on as well. But by default, these are turned off. So once we've created this definition specific to the CSA standard, we would want to apply them to the specific members within the model. And if you remember, the code says to go ahead and apply it to all members. Well, we could graphically select it with this pointer option, or we could use our drop-down box here just to select all. So now that stiffness reduction will be applied to all members within the model. We click OK, but notice my third definition type here that's assigned to my serviceability, we leave this unchecked. We want the full stiffness to be used. We click OK. Under the load combinations, what we see here is that structure modification activated for all of our factored load combinations, but under our unfactored load combinations, that option is turned off. Okay, so now we are complete here with those stability requirements from Annex O. I want to move into the actual steel design add-on. So what we will do here is to right-click and open up our base data. And under the add-ons, we will now activate steel design. So again, everything that you've seen up until now, except for the exception of addressing those instabilities where we use the structure stability add-on, has all been within RFEM alone, including imperfections, stiffness modifications, that's all within the main program. So we're activating here the steel design add-on. Under the standards, you now see steel design available to us here according to the CSA S16. The steel design also has access to all international standards as well. So when you purchase this add-on, you'll have access to the AISC, the EC3, and other international standards shown. The additional setting that I'd like to turn on is under settings and options, we have what's called member representatives, and we get a new tab here. Member representatives are just going to group together similar members that have the same material, the same cross-section, the same length. We even can turn on some of these optional options here, such as the comments, which I have turned on for our model today. So when we turn on member representatives, what we should see here over on the left-hand side is this new option here. Again, where the program has grouped together specific members that are really identical. So how is this going to be an advantage for us? Well, first of all, we've activated the steel design add-on. Let us highlight every single member here within the model. And I'm going to double click on it. A single member, and notice all members are currently selected within this dialog box. But because we have activated that add-on, we have additional options here called design properties, and we specifically call out the steel design add-on. When the design properties is turned on, we have these additional tabs up at the top to define information specific to the CSA standard, as well as information such as unbraced lengths. When we have this option turned off, all those tabs disappear. We are purely going to run an analysis only on those members, so no design. So for now, if I leave all of these options off, we would just be running the analysis only. But here's where these member representatives come into play. First of all, we'll start off with this first group of members. Member representative number 1, it's all of my exterior columns here. I double click on the member representative. Notice that it includes all of these members grouped together here. So if I go into the edit settings for each individual members, I'm going to turn back on the design properties for only these columns, and I get these additional tabs. Now, I'm not going to fill out these additional tabs for each individual member. Rather, when I click OK, I get those exact same tabs under the member representative now. So what's the advantage of this? Well, if I need to make any changes to unbraced lengths, for example, rather than having to select each individual member, make those changes individually, we can go into this member representative and make that same change once, and it will apply it to all of these grouped members together. So we begin with what we call the effective lengths definition type, or unbraced lengths. Now I create my first definition type here. And a little tip is that if we create the first definition type, notice that I don't have any members initially assigned to it. When I click OK and I go back in here to edit that definition type, all of those members are now populated that belong to this member representative. The reason why I do that is now I can toggle this picture here and to actually see a little visibility of each of these members that I'm currently setting these intermediate supports for. So when we're talking about stability design for members, we're talking about flexural buckling in the strong and weak axis direction, torsional buckling, lateral torsional buckling. If we're not concerned with one of these stability checks, we can always uncheck them. The determination of the elastic critical moment, we can use a more theoretical approach, which is the eigenvalue method, where we'll actually take this member, isolate it from the structure, go ahead and run an eigenvalue analysis to determine what that elastic critical moment is for lateral torsional buckling. Alternatively, we can use the user define and input it in manually, or we can use the analytical equations directly from the CSA standard in chapter 13.6. Under the second tab, the top portion here is where I can actually place these intermediate supports on my member. This will automatically calculate then the effective length, which is K times L, in this bottom portion. Now, alternatively, if I want nothing to do with applying these intermediate supports up at the top, we can turn on this absolute values here and to manually input K times L for the member. And this is for flexural buckling, torsional buckling, lateral torsional buckling. The problem here is that if we make any changes to the member, such as the length of the member, we would have to go in and to manually update this. So rather, I want to work with the table up here at the top. So notice that the program automatically detects the member start and the member end nodes. And we have 4 degrees of freedom here, as well as warping considerations. So we have a translation in the strong axis and weak axis. We also have rotation about the member's local x-axis. If I turn this to wireframe view, we see the local axes a little bit more clearly here, as well as rotation about the member's local z-axes. So for this first definition type for our columns, I'll go ahead and leave these as default. Notice the first 3 degrees of freedom are fixed here for my intermediate supports. Now, these intermediate supports have nothing to do with global supports. Rather, we're just using them internally to calculate what those effective lengths should be used, or the unbraced lengths for the actual design according to the CSA standard. So when we click OK, what we should see here now are those intermediate supports shown at either end of the column. Now, additionally, we can apply a local section reduction. So if we create a new definition type here and we take a look at a new reduction type, we can actually decrease the net sectional area if we need to be. So this might be important for something like tension design. We don't have that case today, so we'll just go ahead and leave that empty. So that's fairly straightforward for those columns. But let us take a look here at our third member representative. So notice this group together, these 4 beams here at the outer moment frames of our structure. So those are all identical, and the program grouped those together in that member representative. Well, initially we go into the individual member settings to turn back on the design properties. I click OK, and rather than inputting in the unbraced lengths for each individual member, we're once again going to do it here under the member representatives. We create a new effective length definition type. I can't use this definition type that we previously set for the columns because it's different. So we create a new definition type. Remember the small trick of creating the type, clicking OK, and then going back in simply so that we can see a nice little preview here of those 4 members. So this is a little bit more complex for our intermediate supports under this second tab, because we have additional nodes here, such as where this column and this beam is framing in, that we'd like to take into consideration. This is going to give us more capacity of the member when we're talking about stability design. So we have the ability to turn on intermediate nodes here, and then we can graphically select this member back in the model. And notice that the program automatically detects the intermediate nodes along the member length, where we can apply additional intermediate supports. So we'll begin with this first definition here. So we'll go ahead and leave this as default, where we have restrained these first 3 degrees of freedom. Now, the second node, which we can see here, really means nothing. That node is just to indicate where the transition of our taper begins and ends here. So we'll go ahead and leave all of these fixities empty. The third node, though, is where this member has the column framing up in the strong axis direction and this tube framing in the weak axis direction. So we can go ahead and turn on those fixities here with the first 2 degrees of freedom. And finally, at the peak here, the apex of our structure, same concept. We have that column in the strong and weak axis direction, so perhaps I want to turn off the restraint for rotation about the member's local x-axes. So a couple things to note here. All of these intermediate supports are completely dependent on the connection type. Any software is not going to be able to automatically tell you what unbraced lengths are. It is completely up to the engineer. So we try and guide you here with the locations to apply these intermediate supports, but you'll need to come in and determine which degrees of freedom are fixed or released. The other thing to note is that when we do fix the member in the weak axis direction, we have the eccentricity type down here with this drop down. So we can tell the program if it's braced only at the upper flange, only at the lower flange. If we leave this to none, then the program is going to assume that it's braced at both the upper and the lower flange. So this is nice because in RFEM 5, according to the CSA standard, we always assumed both the upper and lower flange are braced at the same time, but now in RFEM 6, we do give you this capability here to determine if it's one or the other or both. So now that we have defined the intermediate supports for these additional members, the final members that I would like to design are actually these interior beams here. So for the final time, we'll go to our member representative number 5, and we can see the relevant 4 members highlighted here. Once again, we'll go back into the definition settings for each individual member, turn on the design properties, we click OK, and we will go ahead and create our final effective length definition here. Remember, I create the definition type, I go back into edit it so that I get my nice view here of my members. Now, this is going to be very similar to what we just saw for the previous settings. There's just a small difference here. So we do want the program to detect those intermediate nodes so we can graphically select any one of those 4 members. And for the first nodal point here, we'll leave this as the program has suggested. The first 3 degrees of freedom are fixed. Our second node means nothing. The third node here, we do want to only restrain this in the weak axis direction. We don't have any column framing up in the strong axis direction. And finally, at the peak of our structure here, same concept. We only have the weak axis direction restrained. We click OK, and now those effective length definitions are complete. So just to touch on these final 2 tabs here, the ultimate configuration and serviceability configurations. We do have 2 default settings here, but you can come in and create additional definition types or to modify this default. This is just information specific to the CSA standard for ultimate limit state calculation. And we can turn various options on or off here. Under the stability tab, remember I mentioned that U sub 1 factor in chapter 13, that we can set this to 1.0 if we include little p delta effects. Well, we have this automatically turned on by default, so U sub 1 is equal to 1.0 because we do consider p little delta effects. The serviceability configuration, quite straightforward here. We have here our limiting deflection ratio for serviceability checks. So if the member is supported at both ends, we'll use L over 360. If the member is a cantilever, we have L over 180, but you can go in and adjust these limiting deflection ratios as you see fit. The final tab is design supports and deflection. If I do absolutely nothing within this particular tab, the program is going to assume that the member is fixed or supported at the member start and the member end. The full length of the member will be used and will refer to that L over 360. If we have a cantilever, then we would want to define here a design support at the member start or the member end, and then we'll refer to that L over 180. Alternatively, if we have some columns framing up into our members, just to give us a little bit more capacity there with those serviceability checks, we could define additional supports at the internal nodes here. So taking the conservative approach for our example today, we'll just leave everything fixed at both ends, as well as using the full member length. So we're finally done with all of that input data specific to the steel design add-on as well as the CSA standard. We're now ready to run our calculation. One final thing to do under the steel design add-on within our table, notice here that the design situations are listed. We're already familiar with these, and we just simply relate these to the relevant limit state type. So factored load combinations go with the ultimate limit state. Our unfactored load combinations from our serviceability design situation go with the serviceability limit state design. The objects to design, by default, the program selects all members. Notice that we have some members shown here in red, just simply because we haven't turned on the design properties, we haven't defined effective lengths for those. So the program would just give us a small error if we left those in there. Now, alternatively, we can turn off this checkbox and individually set the members and member representatives. Or a nice little tip here is we can just simply hit Control-C to copy these members and then hit Control-V to remove them from the design. So notice those disappear from the not valid or deactivated. We're now ready to run our calculation, so we can simply hit the option here to start that, and the program will cycle through all of our factored load combinations, all of our unfactored load combinations. You can see it run through those simultaneously here rather quick, and we also are running this steel design add-on, again, for that member design ratio specific to the CSA standard. So with the results in the navigator, we have both the static analysis and the steel design. So looking at the static analysis, we can move to any one of these load combinations here just to view, let's say, the applicable global deformations of the structure. We also can take a look at the member internal forces, such as the axial forces or the bending moments, for example. We can right-click on any one of these members, and under the member options, we have what's called the results diagram. The results diagram allows me to turn on and off various internal forces or deflections to see what's going on along the member length in a little bit more detail. We also can move this results diagram to an additional monitor and continue working concurrently in the model, and the results diagram will actually update in real time. All of the information shown graphically is available to us in table format as well. So we're currently viewing this static analysis here, and under our second dropdown, we can view results by member, for example. So if we take a look at the internal forces, we can go ahead and click here in the table. Notice that the graphics are synced up to the table. That red arrow is showing me exactly where that internal force is located. We can export this to Microsoft Excel, do further sorting capabilities. That's all possible here. But additionally, we've also run the steel design at the same time. So we drop down to this option now, and now we can see also within the table, we're currently looking at the steel design results. So we can view the design ratios based on the members or member representatives. If we look at the design ratios by member, we have actually grouped each member here. And again, this table is synced up here with the graphical view to show you, though, every single design check applicable within the CSA standard, not just the controlling check. But if we're thinking, well, I'm really only interested in the controlling design ratio, we can always use our filter option up here in the table to filter to the max. And now only those max design ratios are shown. What else you'll know is that when we're looking at one of the stability checks, we get a deflected shape shown here. This all has to do with that mode shape shown over here in the navigator. Remember, we are designing the lateral torsional buckling based on that eigenvalue analysis. So we actually show you the failure mode here for that eigenvalue mode in order to determine that elastic critical moment. What else is new within RFEM 6 is what we call the design check details. And this is very powerful within the new version here, that we're now giving you all formulas line by line. So you can follow this entirely to determine how that ultimate design ratio was calculated. We're giving you all variables, all code references, how the section was classified. We can see all of that information shown here on the left. We can add these calculations to our printout report as an image. The image will update in real time if we make any modifications to the model and rerun that calculation. So very powerful, and really trying to avoid that black box software and to give you as much information as possible so you can compare to hand calculations and to really understand where the program's numbers come from. One final thing to mention here is the results diagram in section. We can actually view the stresses of the member at this particular X location. So for example, normal stresses due to the normal force, normal stresses due to bending moments, shear stresses, or even von Mises stresses. So if we're interested in the actual stresses of the member rather than just the simple design checks from the CSA, that's all available directly within this same dialog box. Okay, so we will jump back to the PowerPoint to conclude our webinar today. This webinar is recorded and will be available on the same web page that you registered for the webinar. You can download the PowerPoint. You'll be able to download this example model as well. Feel free to open that up in the 90-day trial version of RFEM 6 if you don't already own it. The trial version is full capability for 90 days. It includes all add-ons, and again, you can open up some of these example models. If you have any questions about today's presentation or any of our products, feel free to contact us in our Philadelphia office. The phone number shown here down at the bottom is 267-702-2815, and our email is info-us@deluwald.com. We will have many more upcoming webinars. You can register at deluwald.com under support and learning webinars. As most of you know, I tend to send out a reminder email about a week before these take place, so keep an eye out for those. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So that is a requirement of the states that we are pre-approved providers, that you're here for the full duration in order to receive that PDH. Now, it's not automatic after the presentation ends. It will usually come to you via email within the next day. If you watched with a colleague or you watched in a conference type setting and you did not register for the webinar yourself with your own name and your own email and you are wanting PDH, you will need to request that to info-us@deluwald.com. So again, if you yourself did not register for this GoToWebinar, you will need to request that PDH at the email address shown here. Just let us know who you watched it with and we'll be happy to provide you with PDH as well. And with that said, I want to thank everyone for attending today. And as always, we hope to see you at our next presentation. Thank you.